Dear participants, very good afternoon to all of you. Now we are starting the national seminar.
A very warm, wonderful, and a charming afternoon to every one of you, respected Father Principal, Father Rector, and Father Secretary, our Honorable and most distinguished resource person of the day, our zestful head of the department, cheerful organizing secretaries, cooperative faculties, staffs, and participants from all over the state. I welcome you all to this wonderful session with a very joyful heart. Thank you so much for dialing in with us. I am Joshua from 3rd UG, Department of Physics, St. Xavier's College, Palayamkottai. Now we have gathered here to listen to our most renowned scientist, Dr. Abhishek Kumar, an associate professor and a scientist from the Indian Institute of Technology, Varanasi. He is here with us to feed our appetite in physics. So without any further delay, let us get into the session by opening our lecture with a key of prayer and invoke the blessings of the Lord Almighty. Prayer.
Sweep across our hearts with holy fire. Have your way. This is your house, your home. We welcome you, oh, we welcome you. This is your house, your home. We welcome you today.
I hope our prayer would be listened by the Lord Almighty and may He lead us to the treasures of this session. Having started with the prayer, let us go ahead through a soft welcoming note. I call upon A. Francie from 2nd Basic Physics to welcome the gathering.
A very good afternoon to one and all present here. Sun, the ultimate source of energy, a part of universe with unique characteristic, dynamic power, interesting and mysterious facts behind its structure, origin, and its existence. With immense pleasure, I would like to welcome you all to this national level webinar on the topic, the dynamic sun. First of all, I would like to welcome Reverend Father Dr. S. Mariadoss, SJ, the principal of our college, Palayamkottai. He is a person known for his punctuality, a good supporter, well-wisher, encourager, and a great role model to our students. Hearty welcome, Father. Next, I am very glad to welcome the resource person of this webinar, Dr. Abhishek Kumar Srivastava, the Associate Professor of Physics, Indian Institute of Technology, DHU, Varanasi, a person with a profound knowledge of space science. Hearty welcome, sir. With a grateful heart, I welcome the convener of this webinar, Dr. D. Premanan, the head of the physics department, and the organizing secretaries, Dr. G. David Ratnavelu and Dr. B. Helena, who have made this webinar possible to enrich the minds of the students. I also welcome all the professors, staff members, and the young Abdul Kalams of various colleges who are here. Now, let us listen enthusiastically the knowledge to be imparted by the resource person. Once again, I welcome you all. Thank you.
Thank you, Francie, for your kind welcome note. Now, most of the fundamental ideas of science can be made very easy and simple when they are introduced in a comprehensive and very intellectual language by a great dignitary. Now, I welcome our intellectual head of the department, Dr. D. Premanan, to introduce today's topic.
Respected Reverend Father Dr. V. Henry Jerome, the Rector of St. Xavier's Institution, Palayamkottai, Reverend Father Dr. Alphonse Manickam, the Secretary of St. Xavier's College, Palayamkottai, and Reverend Father Dr. S. Mariadoss, the Principal of St. Xavier's College, Palayamkottai, the organizing secretaries of this webinar, Dr. David Ratnavelu and Dr. B. Helena, the resource person for this webinar, Professor Dr. Abhishek Kumar Srivastava, Associate Professor, the Department of Physics, Indian Institute of Technology, Banaras Hindu University, Varanasi. Good afternoon to one and all. At this juncture, I would like to share a few words on the scope of this webinar. The title of this webinar is The Dynamic Sun. The topic will be elaborately discussed by Dr. Abhishek Kumar Srivastava. Before that, I would like to share a few words on the scope of the webinar. We all know that each day begins when the morning sky gets light. It starts in the east. We first see light at the horizon. That is where the earth meets the sky. We know the sun will rise each morning, yet we hardly ever stop to think about what is happening or why. Have you ever wondered what mysteries the sun holds? So scientists from all over the world are learning more about the sun. The sun is the closest star to the earth. We also know that the sun is millions of miles away. It is so big that 100 earths could fit across it. It is a giant ball of hot moving gases. You can see this in the picture of the sun taken by a telescope. The sun sends energy to the earth and other planets in our solar system. We know this when we feel heat. We know this when we see sunlight. Without the sun, there would be no life on earth. Scientists today study the sun with special tools. They use satellites and telescopes, but sun watching is not new at all. People have been looking at the sun for a very long time. They learned that sun goes through changes, and they used what they learned. It helped them know when to plant crops or get ready to winter. They also learned when the seasons would change. Do you know when the seasons are ready to change? What clues do you look for? Therefore, the sun watchers or the scientists who are discovering a lot about the sun day after day, year after year. They saw that the sun rose and set in a different place every day. They saw that rays of light from the sun hit different places as the year went by. They built windows and doors in special places. These would catch the sun's rays. Looking where sunlight hit made a kind of calendar. It let the yearly sun watchers keep up with important times of the year. To be more elaborate, the sun is the star at the center of the solar system. It is a nearly perfect sphere of hot plasma, heated by nuclear fusion reactions in its core, radiating the energy mainly as visible light, ultraviolet light, and infrared radiation. It is by far the most important source of energy for life on Earth. Its diameter is about 1.39 million kilometers, or 109 times that of the Earth. It accounts for about 99.86% of the total mass of the solar system. Such is the property of the sun. Or in other words, we can say the sun is a G-type main sequence star based on its spectral class. As such, it is informally and not completely accurately referred to as yellow dwarf. It forms approximately 4.6 billion years ago from the gravitational collapse of matter within a region of large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. Therefore, the central mass becomes so hot and dense, it eventually initiated nuclear fission in its core. It is thought that almost all stars form by this process. Therefore, the enormous effects of the sun on Earth has been recognized since prehistoric times. The sun was thought of by some cultures as a deity. The synodic rotation of the Earth and its orbit around the sun are the basis of solar calendars. One which is the Gregorian calendar, the predominant calendar we use till today. So there are a lot of properties about the sun. Therefore, this webinar will pave to understand the important properties and characteristics of the sun. The webinar will be very useful to understand the properties of the sun and characteristics of the sun. Thank you.
Thank you, sir, for your wonderful note. Now it is time for a resource person to take over the mic. Just a moment before that, let me call Dr. G. David Ratnavelu, Assistant Professor from the Department of Physics, who took various measures to conduct this session. I welcome him to introduce the resource person.
Learn from yesterday, live for today, hope for tomorrow. The important thing is never stop questioning, says Albert Einstein. Respected Reverend Father Rector, Reverend Father Secretary, Reverend Father Principal, the patrons of our college, the head of the department and convener of this program, Dr. Prem Anand, department colleagues, faculties and students from various institutions across the country and state, and from St. Xavier's. I'm David Ratnavelu, Assistant Professor and Organizing Secretary, and I welcome you along with the co-organizer, Dr. Helena, the Assistant Professor of the department. Now, with great pleasure and joy, I'm pleased to introduce the resource person, my friend, Dr. Abhishek Kumar Srivastava, the Associate Professor and Organizing Secretary, Associate Professor of Department of Physics, Indian Institute of Technology, Banaras Hindu University, Varanasi. He has completed his PhD work at ITBHU in collaboration with IIA Bangalore in 2006. At this time, I was also doing my PhD, and we got to know each other, and from then on we have become close friends. So after PhD in 2007, he did postdoctoral research work with Professor Doyle from Arma Observatory, Northern Ireland, UK. Then from 2008 to 2013, he worked as a scientist at ARIES, known as Aryabhatta Research Institute of Observational Sciences, Nainital. From 2014 to till date, he is working at IIT BHU. His major research focus are multi-wavelength modeling and observations of transient events like spicules and jets, eruptive phenomena like solar flares, CMEs, and Msd waves and seismology of solar and stellar coronae, and whatnot. He is exploring a lot of things in solar physics. So under his able guidance, 5 candidates have completed PhD, and at present, 4 of them are doing now. And he has developed a research facility called ASCOL, Advanced Solar Computation and Data Analysis Laboratory at IIT BHU. Publications. Our speaker has a distinguished career in solar physics. His research findings are published in more than 127 research articles in reputed international journals. And among them, 3 are published in Nature Astronomy and Nature Scientific Reports. Projects. Astonishingly, so far he has successfully completed 20 national and international level projects to the tune of around 2.2 crores. Collaborate. He has academic collaboration with major scientists across the globe, with almost 11 countries, and also with our many Indian institutes like IIA Bangalore, Ayuka Pune, ISER Kolkata, Aries Nainital, and Calcutta University. International academic visits. As a solar physicist, he is always visiting around many institutions, including USA, China, Italy, Singapore, Poland, and so on, for about 14 countries and more. He has so far organized 14 national and international level conferences and chaired as many as 13 sessions in the same national and international level conferences. Awards and honors. To his honor, Dr. Srivastava has been elected as an editorial board member for about 6 refereed international journals and served as referees for various international journals. He is the lifetime member of several prestigious academic bodies like IAU, namely International Astronomical Union, Astronomical Society of India, and Plasma Science Society of India. He has also served as Senate member of IIT BHU from 2019 to 2021. He was also selected on NASA review panel as a member to review the proposals in solar and heliospheric physics. In 2019, he was awarded the prestigious Lakshmi Narayana and Nagalakshmi Udali Award by the Astronomical Society of India. It's a milestone in his career. So at present, he is serving as a science team member on ISRO's national level study committee for Aditya L1 space mission. You know, Aditya is the first Indian mission to study the sun. For want of time, I have rushed and trimmed down many of his credentials. Pardon me, Abhishek. Dear participants, if you need more details of him, please visit his webpage. And invited talks. Our chief guest is one of the best speakers in the country and has been invited by several prestigious institutes to share his ideas and views. He has delivered 66 invited talks around the globe, including today's talk on the dynamic sun. So with these words, now I invite Dr. Srivastava, my friend, to take over the screen and inspire us through his talk on the dynamic sun. Joshua?
Yeah. Thank you, David. So thank you very much, David, for this nice introduction. And good afternoon, everybody who are here. So it's very nice to present about the sun in this very large gathering. And basically, I would take my time to tell and discuss something which is the general perspective of the sun. So in other words, I would take you towards the journey of our nearest star, that is sun. And I would touch upon some science perspective also in the context of heating and mass transport in the sun's atmosphere. So before going to the talk, I would pose a question here that is sun a very fascinating astrophysical object? So for normal people, the answer generally comes like, okay, sun is very normal star. And every day we see it like a yellow orangish ball. So it comes every day as per, routine manner. So what is fascinating actually? So what I can tell you that sun is very much exotic object as far as the astrophysics as well as space science is concerned. And in modern scientific perspective, the scientists are trying to understand the sun in a very detailed manner. And not even in the modern science perspective, but sun is well studied since ancient time by our ancestors. You know, you're probably aware that sun is explored in different perspective by our ancestors since long time. So as I said, sun is very exotic object. Then you will ask the question, what is the fascinating thing about the sun? Because sun looks very ordinary and it's not changing in our as per our daily life. Okay, so when you see the sun every day, so it looks like like this flat yellow disc. But let's go on the another slide and try to examine something else. You see this is famous Yoko image in 90s, and it is showing the solar atmosphere, which is emitting in terms of X-ray. And once you see this, so you can find out that the solar atmosphere is not now, like a flat disk or something, and it is well structured. You can see lots of emissions are there in the different parts of the sun, and many structures are seen there, and all these structures are emitting basically the X-ray. So the point comes in your mind that, okay, something is going very extraordinary in the sun, that it is emitting in terms of X-ray. And see this is the sun and its atmosphere, which is emitting in the ultraviolet and extreme ultraviolet radiations. So you can again notice lots of structures there, and they are emitting in ultraviolet and extreme ultraviolet wavelength range. So sun is emitting in X-ray, sun is emitting in ultraviolet and extreme ultraviolet wavelength, and so on. And once we go to this image, so this basically tells about the infrared radiations from the sun. So you would notice that sun is also emitting in the infrared wavelength range. And finally, if you see this image, so you would notice that sun is also emitting in the radio wavelengths. Okay, that means if you notice all these slides from the first slide to this one, so you'd probably recall that sun is emitting from the X-ray, and then visible, ultraviolet, infrared, and up to the radio wavelengths. Okay, so that means this is the nearest cosmic laboratory which is well seen in space, and it is emitting entire electromagnetic spectrum. And that is something fascinating. You can get entire electromagnetic radiation from the sun. So then another point comes in our mind, that the range of physical processes which are going on there in the solar atmosphere, and these physical processes are creating different kinds of radiations there. Okay, and then you see this, not only the radiations, not only the entire electromagnetic radiations, but the scientists have observed the emission of or the flow of the charged particles, or stream of energetic particles. Once you go to the pole of the sun at 1 AU, then Ulysses spacecraft with its detector, it is observed the high velocity plasma streams, and its speed is 700 to 800 kilometers per second. We call it solar wind, fast solar wind. And once we go towards the equator, so we find the slow solar wind with the speed of 400 to 500 kilometers per second. So if you collect all the information, so this is very fascinating. Sun is emitting entire electromagnetic radiation, as well as sun is emitting the high velocity particle stream, which is solar wind. So that means it's not an ordinary star or something like very ordinary thing, you know. And this is giving another clue that the solar atmosphere is basically very energized. It is showing lots of dynamical phenomena, a range of physical processes that are forming the wind as well as radiations. And another important clue that is coming is that sun's atmosphere is at very high temperature. Okay, so sun is very spectacular object in many sense. So with these words and with this introduction, I would go to the another slide and try to show you about the anatomy of the sun. See here, this is a cartoon which is telling about the different parts of the sun. So once you focus your attention here in the interior of the sun, so you'd find out that there is a core at the central place of the sun. Within it, and famous nuclear fusion reaction is taking place, where 4 protons are fusing and forming helium as well as energy. And once this energy is getting formed here, this is making the core at very high temperature of 10 to the power 7 degree Kelvin, and radiations are emitting into the radiative zone. And here the plasma properties are set in such a manner that these radiations are doing random work. Random walk means these photons are having very less mean free path of few centimeter, and they are frequently absorbed and re-emitted by the gas. So they took millions of years to reach at the bottom of the surface, which is known as the convection zone. And here convection starts, you know the convection. Convection starts, that means the hot plasma bubble move up while the bubbles they go down and they are circulating. So in that way, due to the convection, they transport heat up to the surface of the sun, which is known as the photosphere. So photosphere is the visible surface of the sun. In some terminology, it can be said like a lowest sun's atmosphere, but in general we call it the solar surface. Okay, so this surface is emitting mostly in the visible, and this is the surface what we see usually from the ground. Okay, and you can see here that there are cone-like structures which are appearing over the entire solar surface, and these cone-like structures are basically the granular patterns. That means plasma is bubbling up and down, and it is creating this kind of cone-like structures. You can also see that there are various these honeycomb-shaped cells, okay, and these are the bigger circulation of the plasma, and they are known as supergranular cells. Apart from quiet sun, there is a polar region, as well as there are the blemishes on the sun's surface, and these blemishes are dark spots, are known as sunspots. Sunspots are the area of very high magnetic field of the order of 1000 Gauss, and they basically constitutes the solar active region. Once you move from the surface of the sun, that is photosphere, so you encounter with the other part of the solar atmosphere. Once you go 500 kilometers and above, so you reach to the chromosphere, and then once you reach approximately around 2000 kilometers, so transition region starts, and thereafter entire thing is corona. And as you can see, once we go from the photosphere to the corona, so magnetic field of the sun dominates, and mostly the plasma is governed by magnetic field. So you can see lots of magnetic structures where either plasma is flowing up, or it is showing some dynamics, or it is trapped there and forming basically the various structures. So you can see here, there are loop-like structures where plasma is embedded in the magnetic field, closed magnetic field. Here you can see the fragmented magnetoplasma system. Here you can see coronal arches. Here at the polar region, you can see the open ray-like structures, which are basically the plume structures. So a variety of magnetic structures are seen in the corona because magnetic field is controlling the entire atmosphere where plasma is there. And it is showing the confined behavior, or it is showing some kind of eruptions also. For example, you see these kind of eruptions are used to take place in the solar atmosphere. So this is more or less the detail of the sun, very primitive and basic details of the sun. But here you see, when we consider that everything is structured in form of plane parallel atmosphere, and once we move with height from the surface photosphere, so you see density drops very fast, this blue curve. And one surprising thing is noticed that temperature was at the photosphere around 5800 Kelvin, and it suddenly rises in the transition region, and it rises in the inner corona up to 1,000,000 degree Kelvin. So that is very surprising. This is the situation like you are having a cold stove and you are putting a tea kettle there and it is boiling. Oh, this is very popular notion. So in other words, the source layer, which is photosphere, that is at 6000 degree Kelvin or 5800 degree Kelvin temperature. And once you are moving up in the corona, you are getting 1,000,000 degree Kelvin temperature only with the distance of 2000 kilometer plus. So this is a huge temperature gradient, and that is basically forming the entire atmosphere of the sun, the corona. And that's the peculiar property of the sun like stars. Okay, so the message is very clear. The sun is a magnetically active star, and sun is basically formed by its very violent and energetic atmosphere. And it is a only cosmic laboratory in our vicinity, which is best observed, and we can test a variety of physics there in terms of observing its radiations and energetic particles and other kinds of dynamics. So basically, we would focus on seeing that how scientific community in general is dealing with the two outstanding problems. One is why temperature of the solar corona is very high, up to the million degree Kelvin, how these winds are generated, and how they are formed and accelerated there in the solar atmosphere. So essentially, they are very outstanding questions since several decades. And you can see here in this animation, okay, this picture, there are a notion that there are lots of eruptions, they are going up from the sun, and there are particles which are going up from the sun, and they constitutes our heliosphere. This goes towards the planetary magnetospheres also. So you can see there is the Earth, and it is its magnetosphere, and these energetic particles and radiations, they are interacting with the Earth, and they are shaping basically its magnetosphere and creating the space weather effect. So understanding of the basic property of sun's atmosphere, its various dynamical plasma processes like origin of wind and its acceleration, various other eruptive processes like solar flares and coronal mass ejections, etc. They are at the forefront of solar research. And all kinds of observatories like the observatories from the space or observatory from the ground, they are trying to figure out the exact scientific cause or exact scientific reason or physics-wise reason behind all these phenomena. So again, I would come to this very illustrative picture. I already told you all that once you are at the core of the sun, so here is the temperature which is very high, and once you go down and reach up to the photosphere, it is going to decrease, and it reaches up to 6,000 Kelvin on average. Fine. So this is as per the thermal physics and its laws. But once you go in the corona, so temperature rises very abruptly, and it reaches to the million degree Kelvin. I already said all these facts to all of you. And this is basically the contradiction of standard thermal physics related laws. Okay. But something fascinating is happening here. Scientists are still trying to figure out about this. There are a variety of observations as well as a variety of theoretical propositions, but still there is no unified picture that why the sun's corona is maintained at so high temperature if it requires lots of energy to maintain that temperature. So basically, why this is happening? So that is ultimate question. For your general perception, I put here one image which is made by me long back. So you can again see, you see this is the sun and sun's western equator. This is a huge area, basically you can see. This is the entire western equatorial part of the limb of the sun. And I made some kind of analysis, DEM analysis. I would not go to the details of all these things. And basically I measured the temperature, and you can see the scale. Mostly the corona is maintained at million degree Kelvin temperature. Fine. At the larger time scale even. But it is not the only temperature that exists over the solar atmosphere. Temperature varies locally. Even if you can see here, there is a kind of flaring region, and temperature rises very, very high. It is equal to log T equals to 7. You can imagine the temperature by converting it to the temperature scale. So with time, the different local regions in the solar atmosphere, they show tremendous energetics as well as kind of plasma dynamics. And all these are related with certain physical processes which are there present. So entire solar community, whether it is in India or abroad, all they are busy in understanding all these aspects of the sun. I hope that these notions are very clear to the audience here. Now I would go and show something which is very unique in terms of solar atmosphere. So once you go to the solar corona, so you would find out that there are basic classifications of the various magnetic regions. And you see here, this is active region. I already told about the active region in my previous slides also. And then rest of the part is quiet sun region. And these black regions where the ultraviolet emissions are very less, they are known as coronal holes. It could be basically at polar regions, but it can extend to the equatorial region also. So let me try to zoom in this, okay? So here I'm trying to show the zoom in part, which is active region. So basically, the sun's atmosphere and its active region is made up of giant closed magnetic field loops, and they are called as coronal loops. So coronal loops are the major building blocks of these kind of regions, and even coronal loops are present in the quiet sun also in form of quiescent loops. And you see, the length scale of these kind of loops are several hundred megameters. So you can imagine the large and very large length scale. And once you go and find out the foot point of these loops, so basically their foot points are anchored over the sunspot groups and the solar photosphere, and they are high magnetic field regions. So in general, the solar corona and its loops, they are anchored in the high magnetic field region, which could be of 1,000 Gauss, but it could be a few hundred Gauss also, or more than 1,000 Gauss also. So they are highly magnetized region. You see lots of heating is going on, and plasma is trapped in these loops. Sometimes it shows some kind of dynamics, sometimes it shows some kind of oscillations, and so on. I would show all these things in my later slides. So message is very clear that if we talk about coronal loops and active regions, so they are basically the magnetically complex regions, and generally the magnetic field is having higher values there. But please remember, their foot points are at the photosphere, and they are having the magnetic field of the order of 1,000 Gauss. But once you go into the corona, it decreases, but still it is high compared to the other regions. And you see, once you try to visualize, okay, without any technical details, the structure of these kind of active regions. So as you're aware that these active regions are associated with the sunspots, which are high magnetic field region. You can read magnetic field value, but in the corona here. So these are basically the sunspots, and they are basically the opposite polarity regions. This is positive polarity, this is negative polarity, and nice magnetic fields are coming out. This is the extrapolated magnetic field by some kind of modeling, and you can see that these magnetic field lines are connecting these opposite polarities. Okay, and once you see similar kind of structures in the closer vicinity in the solar atmosphere, so you can see that these kind of loops are here, and they are also closing from one kind of magnetic polarity to the other kind of magnetic polarity. And you can see lots of fine structures are there. There are a variety of plasma dynamics that is associated with these kind of loops. And these loops, they are requiring certain kind of physical conditions, both in terms of magnetic field as well as in terms of plasma, to sustain here in the solar atmosphere. So probably you are now aware with the active region and its loops. This is another fascinating view of some other active regions. You can see here in this bottom panel that this active region was very complex, and it was having a complex evolution of magnetic field at some part of the solar surface. You see the negative, positive, and lots of magnetic polarities. You know, they are there, and they are sandwiched with each other. And once you go and see in the corona in terms of different emissions, ultraviolet emissions, you can find that these are the loops which are present here, and these loops are having lots of complex structures which is showing heating. So the general notion is that these kind of active regions are very complex, and they possess a multi-temperature plasma, and they possess lots of activity or a kind of plasma dynamics there in these kind of magnetic field systems and related loops. So this is the very fascinating view of active region and their loops. And again, once you go and see and analyze these kind of active regions, so it find out that magnetic field lines are closed in their core and they are forming the loop. And once you go towards their boundary, so you'd find out many magnetic field lines which are going much higher. You know, the magnetic field cannot be, you know, open, so it must close at some distance somewhere in the given domain. So some magnetic field lines are closed in the active region and they're forming the loop structure, core loop structures. Some active region arch-like structures are going up. You see these green fields. So the message is here that these loops, they are not only showing the plasma confinement or trapped plasma, but they also exhibit the movement of the plasma, the flow of the plasma in the upward direction in the solar atmosphere. So they basically contribute to the nascent solar wind, and they basically contribute to the mass cycle of the solar atmosphere. That means mass is not static; it is circulating in the solar atmosphere in different magnetic structures. And you can read out here the Doppler velocity, which is here, and you can see they are a few tens of kilometers per second. That means the plasma flow is of the order of few tens of kilometers per second. So the message is that these active regions are compromised by the high magnetic field region. They are basically made up of the loops, and these loops are having multi-temperature plasma, and they are also associated with the plasma flows there. So this is the introduction of active region. But when you go and try to see the other part of the sun, so basically they are not looking like active region loops. So they are collectively termed as the quiet sun. And once you try to analyze the foot point of the quiet sun region, so you would find out this kind of structures, you know, in overall quiet sun part. Fine. So once you see the top image with care, so you'd find out that there are cone-like structure or granular structures which are present there, and this is present at our entire quiet sun in the solar at the solar surface. And basically they are the manifestation of the bubbling of the plasma or convective motion of the plasma from the convection zone. That means the subphotospheric regions, which is below the surface of the sun, and it is coming out over certain spatial scale of few thousand kilometers with a lifetime of few minutes, and they are coming out and going down, and they appear over entire solar surface. And once they are coming up with the plasma, so they are also transporting the magnetic fluxes, tiny magnetic fluxes. You can see here in the middle part of the image. So these are the systematic magnetic fluxes. They are coming out. White is positive flux, while black is the negative flux, and they come and then they goes down. So they are circulating basically, and they are forming the well-known magnetic network pattern of the solar surface. Basically, they are well pronounced in the quiet sun area. And once you enlarge or zoom in one such patterns, so you would find out that this kind of a structure is seen. So basically, this distance is of, let's say, 10 to 20,000 kilometers, and this area, which is black region area, sometimes it could be positive flux, that is white region also. This is basically the boundary of such magnetic networks, and they are associated with the high magnetic field region. They are associated with the high magnetic field region, while the middle part is at very less magnetic field. So basically what is happening, plasma is coming up, it is bringing the magnetic fluxes, and then after attaining the certain height up to the photosphere and lower chromosphere, it is showing some horizontal motion, and it is going sidewise, and it is transporting entire flux to the boundary, and this flux is basically creating the network boundary. So here is the high magnetic field region, here is the less magnetic field region, and basically this pattern is followed over the entire solar surface where quiet sun is pronounced basically, and it is also found at the polar region also. once you analyze by some kind of modeling these kind of quite some magnetic patches, so you would see that the patches, the part where magnetic field is high, that means at the network region, you know, they are associated with the magnetic flux tubes which is popping up in the solar atmosphere. You can see here, and rest of the part is basically associated with low-lying loop-like structures where plasma could be trapped or confined. And this was a very fascinating discovery, basically, which is made 2 decades earlier. These kind of magnetic patches, when they are existing at the polar region, they are associated with the mass flow in the upward direction. So basically, the strong magnetic field region at the boundary, they may have association with the blue shifted plasma, means plasma is flowing away, and rest of the part, which is the central part, they are associated with the red shift, that means plasma is downflowing. So this paper is published in Science in 1999 by Donald Hassler, and they firstly claimed that these are the networks which are supplying the mass upward in the solar atmosphere, and they might be contributing in the formation of the solar wind plasma flows. And later, this was one of the novel discovery, and this novel finding is again published by C.Y. and Mars and colleagues in the Science, and they found out that at the polar region, these kind of magnetic fields are present, and they are funnel-like structures, and plasma is started flowing somewhere between 5 to 20 megameter in the high. So they did not claim that plasma started flowing from the surface, but they said that it is started flowing somewhere between 5 megameter height to 20 megameter height above the sun. So they have added a very, very extraordinary information in the formation of plasma outflows that may contribute to the solar wind formation. So the message is very clear that sun is not only having hot atmosphere, but it is also emanating lots of plasmas. And these plasmas, they are going up in the higher part of the atmosphere, and they may basically constitute the solar wind. So probably this animation would signify the importance of solar wind. So once plasma is transported to the solar wind, in the far outer atmosphere, in the heliosphere, it propagates and it carries the sun's magnetic field also, and it forms basically the planetary magnetosphere. You can see here, the Earth's magnetosphere is basically shaped by these kind of continuous interaction of solar wind which are coming from the sun. So it is very important to understand the reason of the high temperature of the solar atmosphere, its various dynamical processes, as well as the exact origin and acceleration mechanism of solar wind. Because once we understand all these aspects, so we can understand in a more greater manner the sun and its physics, as well as we can also explore in an exact manner the space weather and other heliospheric physics. So now I would go again to the backward direction. So once we are talking the energy source which can heat the solar atmosphere, and once we are trying to understand about the mass source from where mass is flowing, so we must explore this region. Probably I would not tell the details because this is very specialized thing, but probably you can realize this cartoon. Please just try to read it. So you see, this is quite sun, and this is the strong network magnetic field which is coming up. So you have seen this kind of magnetic field in my earlier slide. And then in between these kind of magnetic field regions, there are field-free regions, okay, which is the central part of these kind of granular pattern or magnetic network pattern above. They are basically forming the cavity regions. And you see a variety of plasma processes are happening. So see, plasma jets are going up, which are carrying the mass. There are wave kind of motions like transverse waves. There are many plasma dynamics which are happening here. Shocks are generating here. There are magnetic swirls which are produced there. And there are many other physical processes like the flow of heated plasma and so on. So please do not go on the details, but try to get the message. What is my message? Message is that once you want to understand exactly the coronal heating problem or mass transport and related physics, you need to explore the layer which is at the bottom of this corona, okay? And that is basically the solar chromosphere. So at the globe, the community is trying to figure out the chromospheric physics also in terms of energy and mass transport. And you see, we are having a variety of observational tools, like we observe the spectra, we observe the images, and we try to capture various kinds of spectrums which are formed in the different regions of the solar atmosphere. For example, this carbon-2 is formed in the transition region, silicon-4 is formed in the solar transition region, and there are magnesium-2 which is formed in the chromospheric region, and so on. There are many coronal emissions also, which is not shown here. So basically, we observe the solar atmosphere by using the imager as well as spectroscopic tools, by capturing the different kinds of spectra, and we try to diagnose the solar atmosphere or different layers of the solar atmosphere, and we try to measure their plasma properties like density, temperature, flow, speed, etc. And we are also trying to figure out the non-thermal motions, etc. there. So this is the other point which I want to describe. You know, there is a requirement of multi-layer observations as well as study, because once, let's say, the wave energy is getting transported in the solar atmosphere, or if the plasma is getting transported in the solar atmosphere, you cannot just rely on the one layer of the solar atmosphere. For example, here is the quiet sun, and you can see here that different layers are observed in different emissions, in different spectral lines, and people are covering from the photosphere, magnetic field measurements, to the upper photosphere, then chromosphere, and the top of the chromosphere. So basically, quiet sun dynamics can be explored in terms of multi-height observations and multi-height study, which can be only done when we observe the different layers of the sun's atmosphere locally using different spectral lines and so on. Similarly, once you talk about active regions, so once you go to the photosphere, you will find out the strongly magnetized sunspot regions, and these sunspot regions are coupled with height. You can see here, once you go to the top of this sunspot, you'll find out many kinds of loops or loop arches. So once you go to the surface, you'll find out vertical umbra's magnetic field. This black region is umbra, and they can act as a large-scale waveguide, transferring the wave energy into the overlying atmosphere. If you talk about waves, so these kind of sunspots, they can act like a waveguide, but they can also transport the shock motions as well as mass can also be flow locally through these kind of magnetic structures. So once you talk about the central region, mass and energy can flow in the vertical magnetic field. Once you go and try to see the outer periphery, which is penumbral region, their magnetic field is bit slanted, and you can still find out the plasma motions there. So sunspots or active regions can have these kind of magnetic structuring, and there you can find out the wave motions, you can find out the plasma motions. They can act as a MSD waveguide. They can transport the magnetohydrodynamic waves there. What are these waves? I would tell in my coming slides. So it is very clear that atmosphere is coupled. When we talk in terms of quiet sun, or when you talk in terms of active region, the atmosphere is coupled in terms of magnetic field as well as plasma dynamics. So we cannot just discuss and study the one layer of the solar atmosphere. We need to constrain the different layers of the solar atmosphere, even in the local or localized part of the atmosphere. Okay. So again, the question comes: why sun's corona is so hot? Why heating is there? Fine. So there are two broader scenarios which are available for the heating of the sun's atmosphere. First is the direct current heating, and this is basically related with the magnetic reconnection, that is dissipation of direct current. So it is proposed long back by using Parker, and even before Parker by many other colleagues like Street, PA, Parker, and other people. And basically, this causes the energy release in the localized solar atmosphere. It can lead eruption and it can contribute to the heating and energization of the corona. Apart from that, we are going to have alternating current, which is AC heating mechanism, and basically they are associated with the magnetic waves. And these waves could force from the photosphere, that is the lower part of the solar atmosphere, chromosphere, or it can be generated in situ in the solar corona. It can transport energy and it can dissipate energy locally in the overlying atmosphere, or can transfer momentum to the plasma and can accelerate the wind related particles. In the nonlinear regime, this can also create the mass transport. I would emphasize all these things in my coming slides. And generally, it can be considered to contribute as a heating of the as a heating candidate of the sun's atmosphere. So, what is MSD wave? So that is another important question. You see this movie. Basically, once you focus on this movie for a while, so it find out there are some disturbances which are here, and these disturbances they are trying to cause the oscillations of this huge magnetic structure, coronal loop. These kind of oscillations are peculiar MSD modes. So what are those modes? I would not go to the details of those modes, but for your information, I can tell that they are kink oscillations. And once you see the chromospheric structures, so you can see here, there are a variety of wave modes that can basically be excited in these kind of magnetic structures. Here you can see there are chromospheric magnetic flux tubes of the length of few megameter, and they are showing some kind of oscillations like this. So this is a kind of torsional oscillation, and they are associated with the torsional alpha wave modes. So they are peculiar MSD modes, and they play an important role for the energization of local or localized magnetoplasma system in the sun's atmosphere. Apart from these kind of waves, you can see here the MSD oscillations. You can see here the torsional waves. Apart from these kind of waves and oscillations, there are certain other kind of physical processes which can present. And you see here, there are two opposite sets of magnetic field lines. They are coming in, and then they are self-reorganizing itself. And this process is known as magnetic reconnection. And this magnetic reconnection can yield energy, can lead the energy generation there in the localized part of the solar atmosphere. And you see the magnetic reconnection here. Basically, the magnetic reconnection is the self-reorganization of the oppositely directed magnetic fields and release of magnetic energy in form of heat. And there is a new type of reconnection we proposed recently, and this is known as the forced reconnection, which is firstly detected by us a few years ago. And you can see here, this is spontaneous reconnection. What is happening here? Two oppositely directed magnetic field lines, they are coming in and they are reorganizing, and here it can release some energy. You see, this is the real observations where magnetic field lines are coming in and they are reconnecting with each other, and some energy is generated here. So this is very primitive definition of magnetic reconnection. It is a full field of research and very famous in some sense. So message is very clear. So in front of our community, apart from many other frontline scientific topics, there are certain very important topics present. And you see, few of them are like, what is the role of waves in the sun's coronal heating? What are the roles of reconnection or forced reconnection in the heating and dynamics of the sun's atmosphere? How the coupling of the sun's atmosphere is occurred by waves and plasma flows? What is the interrelationship of waves and reconnection? And how waves and reconnection can generate plasma flows, and how it can contribute to the generation of the supersonic solar wind or any kind of localized plasma motions or flows. I would show some very novel examples which is done by our group recently. So this is the paper which is published in Nature Scientific Report, and in 2017 we got a very exclusive observation of this part of the sun. And basically, once you go in the solar chromosphere, you find out that this part of the sun in the quiet region, it is containing many flux tubes, magnetic field structures. And these flux tubes are like this. You see, this is the schematic, which is telling that these kind of flux tubes are made up of fine magnetic threads. So this observation is made by 1 meter class Swedish solar telescope. And what we found out here that these kind of magnetic tubes are in plenty there, and they are not the single tube, but they are basically found by the thin plasma threads. You can see thin magnetic field threads. And what was the exclusive observation? The exclusive observation was that the entire flux tube was showing this kind of periodic motion. You see, it appears like blue shifted, one surface is appeared at the left and red is at the right, and then with time this is making some kind of oscillations, like blue becomes red, red becomes blue, and again it is trying to reverse. That means something is doing some kind of oscillation like this, and we are trying to observe this kind of oscillatory motion. So you can see here in the animation, this is the real observation from Swedish solar telescope, which is reported by us. And you can simply notice that these kind of magnetic tubes are oscillating. They are showing the blue and red shift at their surface, and basically they are showing the torsional oscillation. So what is a torsional oscillation? If you have a magnetic tube and if the azimuthal velocity field is perturbed or magnetic field twisting is there, so this could generate some kind of torsional like motion, and this generates basically the incompressible tubular mode, which is known as the torsional mode. I cannot go to the much details, but we have then modeled it, and what we got that this torsional motion is there, is transporting energy, but it is also transporting lots of mass in terms of non-linear behavior. So non-linear behavior of this torsional motion is generating the counter-motive force, which is basically the gradient of magnetic pressure, and this is causing the mass flow also along the tube line. And one very important message is here that this Alphonse wave is carrying the huge energy flux, and this energy flux is the energy flux which is required to compensate the coronal losses. Fine. So it can contribute for the heating of the sun's atmosphere or to maintain or to balance the energy there. And this was the first direct detection of the high frequency Alphonse waves in the solar atmosphere. Before that, there was no such direct imaging or spectropolarimetric analysis present in terms of high frequency Alphonse waves. So later this kind of work got lots of significance, and you can see here that Xavier, Liu and colleagues, they have published Nature Communication paper in 19, and they have detected numerous such kind of torsional motions, swirling motions at the lower solar atmosphere, at the solar photosphere and chromosphere, and they got similar kind of motions that torsional Alphonse waves are propagating. Here is the torsional pulse, and this kind of numerous motions, they can carry energy upward, and they can help in transporting energy and mass in the quiet sun. So you can see here how community is stressing upon all these energy sources, and there are exclusive observations and models are showing that they are able to transport energy in the upper part of the solar atmosphere. So now I would show you a very fascinating finding from our group, which was in 2018, and we are still working on many follow-up studies on it. So what we got, once we got some clues about some kind of wave motion in the quiet sun, and we got the clues that it is transporting energy. So we were trying to check or examine the solar active region. You can see here, you can probably identify now that this is solar active region, and here is the sunny spot, and this sunny spot is basically a single sunny spot, and there are lots of rays which are coming out from the outer periphery of this spot. And what we got accidentally, of course I can say accidentally because we were aiming for the different kind of plasma dynamics, we were aiming for the formation of the jet, but we got very exclusive plasma dynamics here. What we got here, please see. What we got here, over this sunny spot, there are this kind of jets, tadpole-like jets, they are forming. And with time, what is happening? Entire mass of the jet is transported to its head, and this head is looking like a bulky crown-like head. Fine. You see, there are numerous such kind of motions. They are present. Okay, and they are basically the tadpole-like jets, numerous jets which are coming out from the outer periphery of the sun spots. And what they are doing, they are trying to create a crown-like structure at their head. So this was exclusive observation. People had never seen this kind of observations before, and we were a kind of thinking that what could be the physical mechanism. So this is not a normal jet, but this is a kind of jet which is having some kind of physical process there, and we termed this process as a pseudo-shock. What was the pseudo-shock that we modeled by using two fluid equations and models? So you see here in the pseudo-shock, basically this is not the usual shock. What usual shock does, once usual shock propagate in magnetized plasma medium, so it causes the jump in all the quantities like density and pressure and as well as magnetic field and many other quantities which are there. Okay, but here we are not getting any jump in any other quantities, but we are getting the jump or increment, sudden increment in the mass density only. So mass density is there. It is present there at the top of the jet, and basically it was the akin of thermal modes. So non-emission thermal modes are formed at the head of the jets, and they are not propagating, but they are moving with the jet, and they are transporting the carried energy, and they are transporting the carried mass there. As you can see here, there are sufficient energy and sufficient mass which are present, and these energy and masses are enough to basically fulfill the losses, energy loss as well as mass loss in the localized corona. So what we are getting basically, we are getting that these kind of newly discovered pseudo-shock, they can carry some energy and they can carry some mass, and they can compensate the radiative losses in the localized corona. They can transport, of course, some mass to the nascent solar wind, but more studies are required in this direction, and we are still trying to figure out with many other such observations and related case studies. So we are in the process of study more about the pseudo-shocks. So I would not go into the details of these equations, just to flash here. So stringent modeling aspects are involved in these kind of studies. And you see, what is the global implications? You see, in the same year, the UK group has published a paper in Nature Physics, and they also found out the formation of shock, alphonic shocks in the sunspot regions. And what they told that there are some magnetoacoustic perturbations which are going up, and in certain regions where thermal pressure as well as magnetic pressure, they are matching with each other, they are converted in terms of alphonic shocks. So you see, people are trying to understand these kind of mode conversions and the formation of real shocks of the sunspots, and they are claiming that these kinds of dynamics can lead high amount of energy transport, as well as in a nonlinear regime they can do some kind of mass transport also. So this was the story of waves and shocks. Now I would show few glimpses of reconnection. So as I told, we are the first who observed the direct signature of forced reconnection. So what is reconnection? Reconnection, as I already told, that there is a reorganization of two oppositely directed magnetic field domains, where plasma and magnetic field they flows towards a current seat, and what they do, they try to annihilate there and they try to self-reorganize themselves, and in that process energy is getting released. And this energy is basically released here, and this could be a spontaneous activity due to the presence of magnetic diffusivity and or resistivity there. But here in this case, what is happening, there was not any normal reconnection region, there was not any normal reconnection region. What is happening? There was some eruption which is coming from behind. It was trying to push this kind of magnetic field regions. And once this is trying to push these kind of magnetic field regions, so they were going into the reconnection process. So we found this as a direct evidence of the forced reconnection in the solar atmosphere. And we did some modeling stuff also here in support of these observations. And what exclusive thing we found out? So to make a temporary diffusion region or to even make a reconnection, there should be some resistivity and there should be some diffusion region in the localized solar corona. But here it was not the case. Even if we decrease the resistivity, we got a high reconnection rate because we put a disturbance from outside. And you see, once we increase the amplitude of this external disturbance, we get even the high reconnection rate. When we decrease the resistivity, and then we get the high reconnection rate. What is happening basically? This is the basic manifestation of forced reconnection. That means reconnection is not likely in the solar atmosphere, but due to some outside disturbance, it is forced there. For a time being, some kind of current seat is formed there. Current seat is the reason where two opposite magnetic fields are there, present there. And the current seat is formed there for a time being, and it goes into the reconnection and it releases the energy. So this type of forced reconnection could be a important implications, not only in the solar physics, but also in the various other disciplines, like in the planetary physics, in other astrophysical plasma related research, and even in the laboratory plasma also, and fusion research also. So forced reconnection could be a very important science in the coming time. And we are the people who are trying to study this. Earlier, there were models, but now we are claiming the observations. We have recently published another observations of the forced reconnection just in last month, and this paper would pop in soon. So more or less now I would come to the message that what we are trying to do. Okay, so there are plenty of science, plenty of frontline science cases, and basically various kinds of observatories, they are now commissioned, or they are coming in near future, which are trying to stress out, are trying to understand these exclusive scientific phenomenon related to the sun. For example, probably you recognize this. This is Aditya with some its instruments. It is the native mission from the India. It will launch next year. And here is the solar orbiter, which is observing the high resolution corona, and it is already in place. And apart from that, the ground observatories are also there. You can see here 4-meter decrease, which is observing the sun at high resolution. Basically, the solar chromosphere is being observed, and so on. And 2-meter class National Solar Telescope is proposed by the India, and it will soon come into the realization in next 4 or 5 years. And so you see, whole community as a team is trying to the exclusive science by using various kinds of space observatories as well as ground-based observatories. The colleagues are involved in their developments, and many colleagues are involved in the frontline science objects, etc. So the main goal is to define science goals and related inputs to the national missions and international missions, and develop the resources. And it is not only important for the astrophysics or space physics or solar physics, but it is also important for the interdisciplinary applications. For example, you can see here we have observed long back the evolution of kink instability. That means the twisted magnetic field, which is crossing the threshold, certain threshold of the twist, and it is getting destable. And it is mimicked there in the lab by Moser and Bellin in Caltech. You can see these lab experiments, they also obtain the evidences from these kinds of studies in the solar plasma, and astrophysical plasma in more general sense. So where we are basically, we are trying to do the cutting edge observations. We are trying to analyze the cutting edge observations. We are doing some kind of modeling, which could be MSD, which could be multi-fluid, and so on. And we are trying to get the new scientific outputs. And of course, this message is very clear to all of you that we are at the stage, in some sense, that we are trying to explore the high resolution physics. We are trying to constrain the multiple layers of the solar atmosphere. We are developing our facilities by keeping all these things in our mind. And we are trying to combine the various school of thoughts, like whether reconnection is important or waves are important and so on. And we are trying to combine all these exclusive school of thoughts with the cutting edge observations. And we are trying to figure out the scientific studies. For example, here I was discussing about the coronal heating and mass transport process, etc. So the general message is that the solar and heliospheric research and related modeling is tremendously increasing area in Indian and international space science and heliospheric science. This requires the skilled manpower, resources, and working groups across the country, both from science and engineering background. This is the high time to put forward the activities with the involvement of technical institutions, research groups, and new master and PhD students at the national level, and collaboration with the international various teams in the field of solar and heliospheric research. So with these words, I would complete my talk here. And now I hand over the platform to David. David, thank you very much.
Thank you, Dr. Srivastava, for exploring the sun in and out of the atmosphere, as well as even beyond, and for exploring the several factors resulting the long-standing problem called coronal heating, and even more. So now, once again, I thank on my behalf and the department, as well as from the college, with a wholehearted appreciation. Thank you, Abhishek. Now, I will call Joshua to continue the.
Thank you so much, sir.
Yeah.
Thank you so much, Abhishek, sir. We have learned a lot from your session, very inspiring one, and it seems like we got a tour package from here to sun. Now it's time for some questions. Participants, you may ask your questions to our sir through your message in the chat box. You can drop a message there. It seems we have already got some questions. Sir?
Dear participants, if you have any question, please post it in the chat box.
Next question is for the resource person. How does stars born and how long does it take to form a star? How many millions or billions years will it take?
So that depends on the certain criteria. Basically, this is very specialized question. So there are matters everywhere in the galaxy and so on. So basically, at certain region there is a gravitational pull, and that gravitational pull tries to bring in the matter over a certain locus there, and this should follow certain instability criteria. And once all these met together, so basically the collapse of all these masses over one place takes place, and this basically generates the accumulation of the mass. And once it is being done, so this would create the start of nuclear burning, and that basically starts producing the energy and some kind of pressure outward, which is trying to balance the collapse, and then a stable star is getting formed. So basically this is a kind of mechanism which is followed by the star forming regions, and basically you can follow these descriptions. You can find out these descriptions in any astrophysics book. There are genes criteria and other many things which are outlined there. So I hope, I answered up to a certain extent the star formation. And regarding the time, it's a kind of range. I don't remember the exact number, but it takes, a certain range of times. I cannot just comment here, but you can find out those exact numbers there.
Thank you, Abhishek. And
Thank you so much,
Professor
sir.
Dr. Sivaraman is raising his hand. So please have your question, sir.
Hello, good afternoon. Professor Srivastava, your lecture was very nice and it was more informative. And really, it was an eye-opener. I think definitely you will be reaching the solution for the coronal heating. But your observation of pseudo shocks are very interesting. But what you are saying is the sunspots are very important for deciding the sun is whether active or quiet. But your observation is the evaluation of pseudo shocks, which supplies the sufficient energy for the coronal heating, which will be possible only in the case of coronal holes or the sunspots. The sunspots will be more in number only during the active region or active sun. So can you explain the coronal heating phenomena, which is a general feature of the sun, with the help of the pseudo shocks?
Yeah, I understand your question. Basically, there are long-term magnetism of the sun. So basically, I did not touch that aspect. Overall, magnetic field increases at the solar surface with the solar cycle, 11-year solar cycle. And overall, the magnetism evolves in terms of more sunspots and so on. But when we talk about coronal heating, etc., or heat deposition, so generally, we cannot unify the entire sun. So basically, we talk in terms of localized solar atmosphere. Fine. So here, what we are proposing the dynamics over a localized sunspot. And there we find the signature of pseudo-shocks. So basically, it is something like a situation that a strongly magnetized region is appeared locally somewhere in the sun, in the solar atmosphere, and there is suddenly the evolution of this kind of dynamics like jet and the evolved pseudo-shocks. So once it is being done, so it would try to take energy to the overlying atmosphere, which is the local atmosphere, and then it would try to deposit it there. And similarly, it would try to transport mass there in the local atmosphere. So what we told here in all these discussions that they are the candidate which can supply energy and mass locally to the solar atmosphere. And this is very interesting question to find out that how much they are prevalent in the entire solar atmosphere. But it's very hard. It's really very difficult to unify the one physical process. It is in other words, I can say that it is very difficult to find out the presence of a single physical process at the same time over the entire sun. People have earlier proposed that global oscillation can leak. That means they are at the entire solar surface, they can leak and they can transport some energy. But this is very debatable because there are lots of issues that these oscillations are related energies. They cannot leak much higher. They cannot transport energy much higher. So the global phenomena is really a difficult task. So I would say that it is only related with the localized regions. I hope I explained your concern. And
Sir,
rest of the
sir?
thing I already told in my talk.
You're not audible, sir. You're muted. Please unmute.
Okay.
Am
Sir.
I?
Okay. Sir, it was very interesting to observe, get your answer, because I think definitely it cannot be globalized for the whole sun. So
Yeah.
only for a particular region alone, you can, give the reason for the coronal heating. And
Yes.
another one important point which you told is about the reconnection phenomena.
Sure.
That is also very interesting, and that too, when we observe it, actually what happens during the reconnection, it's very interesting to see that. But you are telling that it is externally controlled, which actually the phenomena which controls the reconnection.
Yes. You see, once we try to analyze the reconnection region, so there should be some kind of magnetic diffusion that must present there. And sun's corona is made up in certain manner that it is mostly conductive plasma. So in normal case, the magnetic field lines, they are coupled with the plasma. So they are like a frozen in condition. But suddenly, if certain localized or you can say the tiny diffusion regions are created, so these plasma, they are trying to flow in towards that particular point. And once they go there, they participate in self reorganization, which we term in terms of magnetic reconnection, and the stored magnetic energy is getting released there. So this should be there in some part of the solar atmosphere, but it is generally occurs spontaneously once this kind of condition that meet out there. But here in our example, what we got, that corona was very stable. There was no sign of temporary and localized diffusion and associated magnetic reconnection. What happened? There suddenly some kind of eruption was taking place, let's say from this direction. It was trying to hit this part, and once it was trying to hit this part, temporary current sheet was created. That means one magnetic field domain was created this way and another magnetic field domain was created that way, and there was a kind of separator, and they were having opposite magnetic configuration because this separator was there, and they then go into the reconnection and releases energy. So we termed it as a forced reconnection. Forced reconnection is a very popular word as per the theoretical models, and it is well known in the laboratory plasma, even in controlled fusion experiments. It is well known in the planetary magnetosphere also. But we claimed here that these are the exclusive observations for the first time that are directly seen in the large scale solar phenomena. And then we propose that this kind of forced reconnection must be looked with a care while we are trying to understand the solar eruptions, etc. So still, this is the initial proposal, and as I said, we have continuously studied this aspect in recent years, and hopefully we will have more cases, more elaborations in terms of observations as well as in terms of modeling, and we will try to establish its importance in the solar atmosphere. Thank you.
Okay, sir. Okay, thank you. And I was very much convinced. And only one suggestion. So when you are introducing the torsional oscillations and other things for also the coronal heating phenomena, I suggest you that why can't we take that viscous phenomena also into the consideration, because David is doing more of his work only on viscous plasma. So the viscous drug also may be involving some of the phenomena for coronal heating.
Yes, I think we can have discussion on this. Viscosity is important candidate, especially in the lower part of the.
And you can include it, and you can collaborate with him and do a lot of work.
Sure. So
okay, sir. Okay. Okay, thank you, sir. Thank you very much.
Thank you, Abhishek, for your elaborate answer to Professor Sivaraman. And as we are running out of time, I can shall we take 2 questions max? Abhishek?
Yeah, sure.
Yeah, Ms. Shiba was raising her hand. Ms. Shiba,
I would be happy to answer those questions. There is no problem.
Okay.
I will try
Ms.
my
Shiba,
best.
please unmute and ask your question. Ms. Shiba? Okay. So if she is not available, there was
probably it was written in chat box. You can read from chat box. I would try.
Yeah. So it was some few questions have come in chat box. So probably I will read. Does sun magnetic field strength might affect on solar flares eruption, which might affect on Earth climate? So will the magnetic field of the sun strength on solar flares eruption, will it affect on Earth climate? So that
If
is
I
one question.
understand this question correctly, of course, yes. Magnetic field and its configuration, that basically decides the occurrence of solar flares. So basically, most of the solar flares, they occur from the active regions. So as I said in my talk, that these active regions are constituted by complex sunspot groups, and they could have a magnetic field. That magnetic field would be larger. There may be some more twist that can be accumulated there. So, there could be some preconditions that can build there, that more magnetic energies are stored, and there are likely conditions that can initiate the flare precursors. Okay, and once all these things are there, so there is a chance that flare could happen there. And so the flare occurrence is basically related with the magnetic complexities in that particular region, and energy buildup processes and energy release processes. And of course, once these flares, they do happen there in certain active regions, so they release energy, as well as they could be associated with several other eruptions like coronal mass ejections, as well as a variety of radiations, as I already told. And they can collectively reach to the Earth's magnetosphere and Earth's atmosphere, and they can interact there, and they can do secondary processes, well-known processes, and they can create space weather related effects. And this is one of the frontline science topic which the community is trying to stress out. Even Aditya mission is very much aimed recently to study the space weather effects. Okay, so that could be related to the flares and their effects on the Earth atmosphere. So various its instruments, they are trying to observe flares, like SOOT instrument will be trying to observe flare, and basically it tries to forecast the flare using the observations, magnetic and imaging observations. And VLC on the Aditya, it will try to learn the CME propagation and will try to estimate various its properties, including the arrival time, etc., at the 1 AU and so on. And then other in situ instruments are there, like X-ray instruments and so on. They would try to understand the X-ray radiations, etc., which are coming towards the Earth. And basically, one of the aim is to figure out the flare, forecast the flare, study the CMEs and their space weather. So it's very nice question. So it is a very much challenging problem to understand the necessary condition to build the flare energy there. Okay, so when certain region will build the flare energy, that would be a very important topic, and that would initiate us or enable us in predicting the solar flare or occurrence of solar flare. So very fascinating field of research, and really, people are trying to understand it.
Thank you, Abhishek, for your elaborate answer. And there is an interesting question. I don't know whether it is related to solar physics, but maybe you can comment on it. What happened to the sun during the ice age in Earth? Is a question.
Many people believe that there was a kind of there was many ice ages. Sorry for the deviation, but I believe that you are talking about the ice age which is around 1600 AD, not the main ice age. So there was a mini ice age around 1600 AD, and that was the time when entire Europe was frozen with ice, and even Thames River was frozen and so on. People were walking on the river and so on. So on that time, there was the observations that sunspots were minimum at the sun, And this is known as famous Maunder minimum period. So some people, they try to connect these two events, like the solar activity was minimum. So on that time, there was a kind of mini ice age at the Earth, basically in the European part and so on. But there is not a very firm ground to connect these two things. But thanks to the recent observations and big cohort of the data, even atmospheric size data and solar data, that now many people, they are trying to understand the effect of solar activity on our local weather, like what we have. And they are trying to get some kind of connection, but still this is in primitive stage and in very preliminary stage, and people are still trying to figure out what's the exact cause. But there may be some.
Thank you. Yeah. Thank you, Abhishek. And we will take the final question. Can we utilize any energies from the sun reaching the earth for future harmless communications of network? For example, aurora, plasma, alpha waves, magnetic waves, etc.
People propose something like we can trap the particles and we can find out some energies, but I don't know exact answer, because personally I don't find it very much practically possible. But anyway, solar radiations are used for many purposes. This is very important. If we could trap some energetic particles and we could use it for some uses, that would be great. Research could be done in this direction, and few people are trying to do it, but maybe I don't know the exact answer, but that what they are doing. Probably there are some research, but this is very specialized, so you can go and find out those informations.
Yeah. Thank you, Abhishek. I know it is beyond the regime of the solar physics. It is related to the communication and etc. And I sincerely thank your patience on answering such questions. Now let me hand over the session to Joshua. Joshua, please continue.
Thank you so much, sir, for your awesome and thought-provoking session. Now we have come to the end of our webinar. It will not be fair to conclude our session without expressing our gratitude. So now I call upon Master M. Anto George from second UG Physics to give us a vote of thanks.
Gratitude is a quality similar to electricity. It must be produced and discharged and used up in order to exist at all. I deem it a great honor and privilege on behalf of the organizing team to propose the vote of thanks on this occasion. Let me start by giving glory to the Almighty God for making today's webinar a resounding success. I'm grateful to our Reverend Dr. S. Mariadoss, SJ, Principal, for his spiritual guidance, his kindness, his interest, his hospitality, and continued support. Thank you, Father. I express my deepest sense of gratitude to our resource person, Dr. Abhishek Kumar, an Associate Professor of Physics, Indian Institute of Technology, PHU Varanasi, for gracing his important work and sharing with us his findings and opinions today. Thank you, sir, for the excellent presentation and for making this webinar a very interesting and meaningful one. I would like to take this opportunity to express my heartfelt thanks to Dr. D. Premanand, the convener and the head of the department, for his enormous support and guidance in organizing this webinar. Thank you, Professor. My heart goes out to thank Dr. G. David Ratnavelu and Dr. B. Helena, assistant professors and the organizing secretaries, who have provided their minute-to-minute of support and guidance for encouraging at every point of time to enrich this webinar. Thank you, professors. I also wish to express my gratitude to Ms. Francie of 2nd BSc Physics for her warm words of welcome. Thank you, Francie. I extend my thanks to Mr. M. Joshua of 3rd BSc Physics for his efforts towards today's anchoring. Thank you, Joshua. My heart fills with lots of gratitude and respect to all our department staff for not only sparing their invaluable time for us to grace this webinar, but also for best efforts to make this webinar an unforgettable one. Really, we are highly obliged. Thank you, professors. No event can happen without the provision of a vast network and people. An event of this dimension can happen overnight and needs meticulous planning and execution and an eye for detail. I cannot thank each one enough for the involvement they have shown and the willingness they have expressed to take on the success of this webinar beyond their comfort zone. Last but not the least, I thank the participants of this webinar in making this program a huge success. Once again, I thank you all for your attention. Thank you.
Thank you so much for coming to this wonderful session and making use of it. Thank you all.
Thank you, Abhishek, for your valuable, spending your valuable time. Very happy to see you. And Professor Sivaraman, you know, so he's my supervisor, research supervisor. So I specially invited him to talk to you, and he did it. Yeah. So shall we wind up?
Yeah, sure. Thank you very much.
Okay.
Thanks. Indeed.
Yeah.
Bye.
Okay. Thank you so much.
Thank you,
so much. Abhishek, he is the head of the department, Dr. Premanand.
Yeah.
He is thanking you for
Thank
your,
you very much, Dr. Anand. Thanks for all this gesture, and I enjoyed this talk. So and this gathering. So hopefully we'll meet somewhere in some conferences or somewhere.
Sure, sir. Sure.
Okay, David.
Okay.
So
Okay.
should I go out now?
Sure. Yeah. You can. You may log out, and we will make the thing officially closed. Thank you all.
Okay. Bye. Take care.
Bye.